Good. Thank you very much, Andras. Well, thank you all for coming back for round two. So let me remind you what I did last time and plunge ahead. So we were talking about the general problem that we start with some space which is non-compact or singular, and we have an elliptic operator in it, and for illustrative purposes, I'll mostly talk about geometric elliptic operators. So I'll start with some manifold, and I have some Laplace-type operator, which I'll take to be just Laplacian for simplicity. And I'm interested in understanding various analytic properties of the Laplacian. So the types of things you might ask are, what are its mapping properties? What spaces is it pretty well behaved acting between? I mean, ultimately, let's face it, the thing that we want to do is solve Laplacian U equals F, right? That's the basic problem of mathematics in one guise or another. So, So, what are the things you'd like to know? Well, given f in a certain class of functions, can we solve it? Or does the operator have some horrible property like, it doesn't have closed range or something? Remember all the horrible things that can happen in infinite dimensions? So you'd like to know what function spaces is it acting nicely between? And then what are the fine regularity properties of functions? If I know that f has some very specific decay properties or regularity properties, then what are the precise properties for u? And as I explained last time, there are these 2 points of view that you're all familiar with. One is the a priori estimate point of view, and the other is the parametrics point of view. And they're equivalent, but I'm arguing for the primacy of the parametrics method as being more flexible. Okay, so what we were looking for the Laplacian is, okay, so let's take the Laplacian. So what I'd really like on this given space is I'd like to find an operator G. So remember, I start off with an operator, then there's this great abstract theorem, the Schwarz-Kernel theorem, which says that any operator corresponds to a distribution on the product space. So I'd like to solve Laplacian G is equal to the identity is equal to G times the Laplacian. This would be the ideal state of affairs because then, well, if I had that, then I can just write down U is equal to G of F. Well, that hasn't solved my problems, but what it tells me is I better understand what this is. Now, as an integral operator, this means I'm looking at this sort of thing. So I'm using the volume form on the manifold, let's say with respect to the Riemannian metric. And let me sort of start to phrase this in slightly geometric language, which I'll be using more extensively soon. Here's a copy of M cross M. This G is a distribution on M cross M, and it has the property that it is singular along the diagonal. So it has what I'll call a standard classical pseudodifferential singularity along the diagonal. Or prosaically, it's looking like the Newtonian potential. It looks like distance to the power 2 minus n as you approach the diagonal. And then it's doing something in the far field. It's doing something as you move a long ways away from the diagonal. And as I explained yesterday, that's really what interests us. That contains a lot of geometry. Okay, and so here's sort of the z axis. Here's the z tilde axis. What am I doing? I have this distribution G. I have some f, which I'm sort of pulling back to these fibers, and I'm integrating down. So I'm doing something that looks a little bit funny, but let me write this in objectionable language. So I want to take, so I have 2 projections from M cross M to M, the left and the right projection. Okay, and so what I'm doing is I'm taking on the right, I'm pulling back f on the right. Okay, so I'm thinking of it just as a function of z tilde. I'm multiplying it by this Schwarz-Kernel, by this distribution. So now I have a distribution on M cross M. If f is smooth, then this is a perfectly good thing. If f is not smooth, then you might have to worry a little bit about taking a product. But of course, the wavefront sets don't meet, so you're in good shape. And then I take the push forward, pi L push forward. So this is equal to u. Okay, that's a bit of a funny way of just writing that integral formula. But I want to take advantage of that later on. Okay, so that's the kind of thing that we're trying to analyze. Now the question is, can we find such a distribution? Now the whole point of the parametrics method is that typically it may be hard to find such a G, at least except for in rare cases you can't just guess it or write it down. I showed like one case where you could in hyperbolic space, where you could just write that down exactly. But more generally what you can do is you can find a G tilde, which is an approximation. So namely, it'll solve something like the following. Laplacian G tilde is equal to the identity minus R1. G tilde minus times the Laplacian is equal to the identity minus R2. So this is what we call the parametrics. And the whole point of this was that we want the error terms to be as small as possible. So the ideal situation would be 0. The next most ideal situation would be these would be finite rank operators. And, well, again, that's kind of hard to engineer at first guess. But what we can try, so we can try to find, so the easiest, and let's just say this is standard pseudo-differential operator theory, is that R1 and R2 are smoothing. So that means that they're pseudo-differential operators of order minus infinity. Or in other words, if I look at these Schwarz kernels, Rj of z and z tilde, these are C infinity functions on m cross m tilde, m cross m. Okay? So all I'm doing is I'm applying the symbol calculus and the elliptic parametrics construction to solve away the singularity on the diagonal exactly. I gave you yesterday a very crude form of this, which is the Audemars parametrics formula. And oscillatory integrals in the Fourier representation of pseudo-differential operators give you a much more clean and systematic way to do that. Okay? Okay, so better. So now the point is, this gives you local regularity theory, but it tells you nothing about Fredholmness or global mapping properties. So for example, suppose I had F being smooth compactly supported. I want to know, what does the solution look like? What does it look like in the far field? This tells you nothing, or nothing useful in any case. So better would be, for example, if Rj, well, so let me give you a type of mapping property that might be very useful. Rj maps L2, for example, into a weighted space, and let's just say, let me call rho as some sort of generic distance function from the origin or from a compact set in the manifold M, to some fixed, let's say, r to the k times h infinity. So any Sobolev space. It's smoothing, so the regularity isn't the issue. But the point is it gives you some extra decay. Okay? So now what does that mean in terms of Schwarz kernels? So if I look at the Rj's, well, it's smooth. It has nothing happening along the diagonal, right? But what it's saying here is if I put in anything in L2, then it gives you something which decays. So roughly speaking, that says that as I go in these directions, the kernel has to decay. Okay? Well, or maybe just as I go out to infinity in the diagonal or something like that. So, for example, it's not hard to engineer that I find the G tilde and the R1 and R2 that are supported just in a distance one neighborhood of the diagonal. So this is kind of what standard pseudo-differential operator theory will do for you. I can make it properly supported, as I guess the term. But then I'd like it to decay, the error terms to decay in these terms. So what does this do for you? Well, it means that, for example, so this is going to imply that Laplacian is Fredholm. Okay, why is that? Well, it's the usual kind of proof, but let's just say for the null space, if I have something in the null space, if I have Laplacian of u is equal to 0, this is going to tell me that u is equal to, let me see, which way do I do it? I take this thing, I apply both sides to u, and I'm going to get u is equal to R2 of u, and I use the fact that R2 is a compact operator, so it takes something in L2, so u is in the L2 null space. Okay, and it's going to tell me that u is equal to R2. So this immediately says that u is smooth because it's equal to smoothing operator applied to u. But more to the point, it tells me that u has a definite rate of decay, right? So let me say that very specifically. Take the unit ball in L2 intersected with the null space. This says it's going to map into a compact or a pre-compact set in L2. So it's finite dimensional. Okay? And so there's all sorts of applications. So this is, as I say, the heart of the Hodge theorem. So the minute you know it's finite dimensional and you have some specific rate of decay, then you can do all the normal integrations by parts that prove the Hodge theorem. Okay? They're really just formal, essentially just linear algebra, once you have this closed range in Fredholmness. Excuse me? I usually think of rho as being distance from infinity, so. Yes, okay, so forgive me. So if rho is distance from a point, then I'd want k to be negative. I gives decay. Or if rho is like distance to infinity, as I said, like e to the minus r, like I was talking about yesterday, then it should be positive. Thank you for pointing that out. Okay, so anyway, that's the basic scheme. Now, I was talking about this, this model problem. Well, let's say a test case. And I was talking about it in increasing generality. So this was the Laplacian on hyperbolic space, and slightly more generally, I'm going to take the Laplacian minus s times n minus 1 minus s on Hn. Okay, now maybe somebody who knows more than I will tell me if I got that sign right. So this is the Laplacian, so this is the hard part. I'll tell you what the formula should be, then that's your homework to figure out if I got that sign right. Okay, now why do I do this? Well, this is just Laplacian minus lambda, but I've written the spectral parameter in a funny way. So the analysis of this operator, well, the thing that I really am interested in is inverting it, Laplacian minus lambda inverse. This is the resolvent, and one of the first things that you'd like to do is understand, well, when does this exist, for which lambda? Do you get sort of beyond the fact that Laplacian is sort of self-adjoint and semi-bounded? And ideally, you'd like to know things about what happens to the spectrum. Can you analytically continue past the spectrum, and blah, blah, blah. There's a lot of stuff there. So I'll say some of the theorems that one can prove in the fullness of time. But so for reasons that are purely for notational convenience, I write the spectral parameter as s times n minus 1 minus s. Okay? Now, I had several layers of, so I want to run through this parametrics construction and ask this basic question about, can I solve this equation, not Laplacian, but Laplacian minus lambda of u equals f. So can I solve that on hyperbolic space? Okay, well, as I described, this g, and I'll write it as g sub s now. Okay, this solves, okay, well, it's going to be dr squared plus, now there's going to be an n minus 1 cosh r over sinh r dr. GS only depends on r. Remember that it's a point pair invariant, so it only depends on the distance between 2 points, and it's rotationally invariant. So it effectively reduces to a function of one variable. So dr. And now here's the acid test case. So minus s times n minus 1 minus s, all applied to g sub s is equal to 0. Okay. And as I go towards infinity, so I change variables to rho is equal to e to the minus r, I'm going to get sort of a regular singular type problem. And what I'm going to get is that g sub s is approximately going to look like rho to the 0 or rho to the n minus 1 as rho goes to 0. So that's just sort of a formal ODE analysis.
Isn't there some Laplacian in that?
Well, except for that's so g sub s only depends on r, so I can omit the spherical Laplacian. Okay, good point. Okay, so it solves this ODE. I can write down the solution. In fact, I can really write down the solution. So in 3 dimensions, here it is. So in n equals 3, g sub s is going to look like e to the minus s minus 1 times rho divided by sinh of rho. Okay, so that's an explicit solution. And in general dimensions, there's something like this where I take derivatives or fractional derivatives of this. Okay, so okay, there it is. And the thing that I said yesterday, and I'm going to say much more carefully now, is that if I transfer this to rectangular coordinates, so I use the upper half space model, x and y. Here I'm going to have x tilde, y minus y tilde. So I'm thinking of this g sub s as a function of x tilde, and y minus y tilde. Okay, this is dilation invariant in these variables. So this is equal to g sub s. Well, let me see. I've already used lambda. So what's another good dilation in variable? Let's call it t. So no, that's a bad one. Beta. There we go. That's a great one. So beta x tilde, beta of y minus y tilde. This is for all beta greater than 0. Okay. Okay. So there we have it. And what that means geometrically is that on all of these rays coming out of the, well, this neighborhood where all of this is 0, this is constant. So what that means is that this thing is somehow only depends on the spherical angle here. Now the way we represent that is we perform a blow up. So we blow up the submanifold x equals 0, x tilde equals 0, y equals y tilde in M cross M. Okay, now M here is just hyperbolic space, but let me keep the sort of same general notation. Okay, so I'm going to obtain a new space, and I'm going to call this M20. So this is, here's some notation, M cross M, and I'm going to blow up at this submanifold, which I'll call S. Okay, now what does blowing up mean? Well, so here's a picture. Here's S sitting inside some bigger manifold. It turns out that S sits inside a corner of M cross M, because remember, M is a manifold with boundary. So M cross M is a manifold with corners of codimension 2. So it has this, it's like a sector in R3 in this picture. So if I blow up S, what I'm doing is I'm taking every point of S and I'm replacing it by its normal sphere. Okay, so this is sort of a picture of an interior S. So I am replacing a line by a garden hose, right? So every point is replaced by the spherical set of normal vectors. Okay, now one way to say that is I'm taking cylindrical coordinates and I'm adding the r equals 0 cylindrical face. Anyway, there's all sorts of fancy ways to say this. This is just a blow up. It's a real blow up as opposed to the algebraic geometric complex blow ups, okay, where you don't get introduce a boundary component. So the point is I'm going to have a face, a front face, which is sitting over S. This fiber's over S. Each fiber is a sphere in this case. And in this picture, when I blow up that thing, I'm going to get this picture. So I'm going to get, so this is the space M20. So here is sort of this front face, right? And so remember, I've suppressed a dimension here, which is, well, really, I have the y tilde variable, which I'm not picturing there. So I really have this new boundary face, which is fibered by quarter spheres, okay? And the diagonal sits here, okay? And my basic statement about this particular G sub S is that it's independent of the y tilde variable, so it only depends on y minus y tilde. That just reflects, that's an isometry in hyperbolic space, so it should be a convolution operator in those variables. It's singular along the diagonal, right? And so what do I know now about on this face? Well, along every single ray here, it's sort of constant, which means that in the most trivial possible way, it's smooth up to the front face. Okay, so it's smooth in this direction, right? What happens as I go here or here? Well, I have to go back to, this formula or, this formal analysis or something like that. Okay? Well, what is happening is as I go towards this face, now I'm going to say slightly misleadingly, I'm going to say that it looks like x to the n minus 1 as I go to this face and x tilde to the n minus 1 as I go to that face, and like r to the 0 as I go to that face. Now, what am I really saying? Well, there's some boundary defining function. So some function which vanishes on that boundary but not on the other boundaries. And in terms of that, it vanishes like x to the n minus 1, x tilde to the n minus 1, and whatever the boundary defining function to the power of 0 here is smooth up to that. That's my basic regularity statement. Okay? Now, why is x a bad variable? Well, if I take x on this space and I lift it up here, it vanishes here and here. Right? So really, I'd want to be taking whatever the right, x divided by r as a good defining function. Okay, is everybody clear on that? That's sort of a key fact. Now, somebody asked me before the lecture a very good question, is what happens at infinity? And the point here is that there is no infinity, just how I drew the picture. Remember, M is a ball. M is hyperbolic space. Okay? And so I, when I take M cross M, well, it looks schematically, a ball across a ball looks kind of like that, right? And, well, anyway, that's a slightly misrepresented picture. Then I'm blowing up this piece of the corner at infinity, okay? Or, at the corner. So I'm blowing up something inside of here. Okay, so that's the general picture. So what I'm doing here is I have an operator which is degenerate. And at least in this model case, what I've done is I've seen that the solution operator, which I found just by ODE analysis, lives naturally as a very nice distribution on this thing. Now, forgive me, for Laplacian, I have x to the n minus 1. Here's the point which I didn't say. Suppose I look at solutions of this. So somebody didn't scream, so forgive me. It's your fault. You know better. So this is wrong here, right? So there are two possible solutions. One, I've added the spectral parameter. The point is it can look like rho to the s or rho to the n minus 1 minus s. That's exactly why I've sort of made the numerology that way, why I wrote the spectral parameter as this product. Okay? Do you atone for your sins? Yeah. Okay, so the point is that I want to look in a region where S is big, so I'm going to map into L2. So I'll look in the region where S is bigger than n minus 1 minus S. Or in other words, S is bigger, and let me sort of say emphatically, the real part of S is greater than n minus 1 over 2. So I'm going to look in that region where the real part of S is greater than n minus 1 over 2. And then I don't look like x to the n minus 1. I look like x to the s and x tilde to the s. Okay? So what I'm doing is I'm choosing the solution of this ODE that behaves like the good solution at rho equals 0, and it's behaving like r to the 2 minus n as r goes to 0. Okay? So I'm sort of saying what's happening at 0 and infinity. This is infinity. This is at 0. It looks like an ordinary Green's function. Okay, so this is now my model. I've, in this particular case, written down an exact solution. I've told you the exact regularity properties of this. Now, let me say a little bit more specifically. When I say it looks like x to the s, what am I really saying? What I'm really saying is it looks like x to the s times a smooth function. And let me say that even more separately. It looks like, actually, some series that looks like x to the s plus x to the s plus 1 plus x to the s plus 2, etc. So it's a function. Well, it's a distribution, but its singularity is just right here, so I don't have to worry about that. As I go to this face where x is vanishing, right, it has an asymptotic series in the classical sense that starts off with x to the s and then goes up in integer steps. Okay? And that's the natural regularity. Now, what would that tell me? So suppose I'm trying to solve Laplacian minus s times n minus 1 minus s of u equals f. And let's suppose, for simplicity, that f is in C infinity 0. Okay, so what am I doing now in terms of this picture? So I have, let me try to draw it in terms of this picture. Here's this thing. Here's x tilde. I'm pulling back f to only depend on this variable. So f sort of, its support is compact in the x tilde variables. So its support is, let's say, in some blob here, but then it extends out here once I pulled it back. Right, so in some sort of cylindrical region. So its support is compact in here, away from the boundary, and then I pull it back, so its support is here, and then I push it down, I integrate. Okay? Now when I integrate, things are non-zero everywhere, so I'm going to get some function which is non-zero everywhere, which is not particularly shocking. You know, my solution is global, right? It's not going to be compactly supported, typically. Okay, so I'm going to have u is equal to g sub s applied to f. It's going to be that guy. What this analysis will tell me is that this thing will look like, as I go towards the boundary, it's going to look like x to the s plus higher order terms. Or maybe said a little bit differently, it's going to look at like some function a of y times x to the s plus higher order terms. And if you keep track of the full expansion of this solution, where s is bigger than n minus 1 minus s, the ODE solution actually has two asymptotic branches. One that starts with x to the s, and the other that starts with x to the n minus 1 minus s. So that's just from ODE analysis. These are the two initial roots of this regular singular problem. And I'm going to get plus dot 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 plus b of y times x to the n minus 1 minus s plus higher order junk. So the point is, it's not going to be x to the s times the smooth function, so I lied, right, as usual. But it'll look like the sum of two functions, one of which is x to the s times a smooth function, the other of which is x to the n minus 1 minus s times another smooth function. And I've just written out the leading terms of those two smooth functions. Now, for those of you who are more analytically inclined, this should look familiar. So in fact, what I've done here is I've told you what the scattering operator is in hyperbolic space. So the operator, which we'll call capital S of little s, is the operator which takes a of y to b of y. So that's the scattering matrix. The scattering operator in general. Okay? So it's an operator acting on functions on the boundary. So a can be, a will be a function on the boundary, and b will be a function also on the boundary. So it takes one function on the boundary to the other. Okay? Now this is kind of an odd form of the scattering matrix because it's sort of relating these two leading coefficients, and sometimes you might formulate it as b going to a, or some. So the point is that we're going to be able to do this. So remember I drew the S-plane where this complex parameter s lives, and I said there was some sort of mystical line n minus 1 over 2, and I initially start off with the real part of s bigger than that line. This is the so-called critical line. Okay? It's going to turn out that this parametrics method, well, in this hyperbolic space case, I immediately can continue. This solution to this ODE is entire in S, or meromorphic in S. Okay? So it continues across to this side. Actually, there may be a branch point somewhere, but that's leave that aside for the moment. So it continues to this, or the logarithmic cover of this plane. And over here, this is sort of the better term at infinity. Over here, they've switched roles. Okay, so this guy all of a sudden becomes the more decaying one. Right on the critical line, when s is equal to n minus 1 over 2 plus an imaginary number, so if s is equal to n minus 1 over 2 plus I mu, then n minus 1 minus s is equal to n minus 1 over 2 minus I mu, and the product is equal to n minus 1 squared over 4 plus mu squared. Okay, so what that's going to tell me is that these two values, s and n minus 1 minus s, when s is on this critical line, have exactly the same rate of decay. They're just oscillating in opposite ways. Okay? And that's what the scattering matrix traditionally is. I take sort of the incoming solution and it maps to the incoming Sommerfeld radiation data, it maps to the outgoing one, or vice versa. Okay, so again, that's something you can do just sort of very explicitly in the hyperbolic case. Now, let's talk about the successive levels of generalization that I mentioned. So the next case is, let's suppose I'm doing this on, let's say I have Laplacian plus v minus s times n minus 1 minus s, where v is c infinity 0, or slightly more generally, or v equals 0, but I work on hn minus a compact set. Okay, but I want to think about this because it's sort of a variable coefficient version, but this is just like a compact perturbation. You can think of any sort of black box compact perturbation. Okay, so the point is the following, that I no longer can find an exact solution. So once again, I'm going to want an exact function g sub s. I want to take Laplacian plus v minus s times n minus 1 minus s is equal to the identity. Well, what is the identity? It's the delta function. So I'd like to solve that question. It's no longer an ODE analysis, but what I'm going to do is, well, at the crudest level, I can do exactly what I described yesterday. I can find a parametrics by, I can say that this g sub s is approximated by, well, I'm going to take this chi1 tilde g sub in chi1 plus chi2 tilde g sub out chi2. So this g sub out is exactly the g sub s on hn. Okay? Because on hn, outside a compact set, there's nothing going on. It's just the potential is 0, and that, that looks good. So what this chi2 is, so here's hyperbolic space. Chi1 and chi2, they're sort of supported here and here. Of course, it's a partition of unity. Chi1 tilde is 1 on the support of chi1, but it's still, just like I described yesterday. So what this guy does is it says, take an f, localize it to here, apply some, well, inverse, or ideally just some local parametrics, just living on a compact set of hn, but to the operator Laplacian plus v, genuinely variable coefficient. Okay? And then relocalize to the interior. So that's that bit. This guy says, localize to the exterior. There it's just the Laplacian. Nothing interesting is going on, just the Laplacian. I know the answer, g sub out, and then relocalize to the exterior. Okay, now the point is when I do those two things, I'm going to get a good parametrics. I can see what the error terms are quite easily. So suppose I take Laplacian plus v minus s times n minus 1 minus s, acting on this g tilde sub s. I guess I called it. Well, so there's going to be two bits. There's going to be the first bit where I hit this guy, right? And there's going to be a chi1 tilde times this operator. Maybe I'll just call this L for simplicity. L applied to g interior times chi1 plus chi2 tilde L g out chi2. And then there's going to be two other terms which come from commuting the operator past these cutoff functions. So plus L commuted with chi1 tilde, g in chi1, plus L commuted with chi2 tilde, g out chi2, right? So that's the full thing. That's an equality. Okay. What do I know about this guy? This is the simplest guy. I mean, the exterior region, I found an exact solution. So that's just the identity. What about this guy? Well, it was just a variable coefficient in the interior, problem in the interior. So I didn't find an exact solution, but what I could do is I could solve LG interior is equal to the identity minus maybe, let's say, some Q1, where this Q1 is C infinity. Okay, so I find a good pseudo-differential approximation to what the inverse should look like. Okay, so I plug that in here, so I'm going to have the identity, but then I have this extra bit, this smooth bit, and then I'm going to have these commutator terms. Okay, so I'm going to leave it for you as a bit of homework to just check that, well, so the claim is G sub s tilde is smooth, and I'll clarify that term in just a second, on the same space, M2, 0. So this is M cross M blown up at that submanifold. Okay, so I have this space, which I'm drawing figuratively like that. Okay, there's some sort of interior compact disturbance, but I can look at these two things, and everything is behaving extremely well. Right? Furthermore, if I take this L G sub s tilde is equal to the identity minus R1, G sub s tilde L is equal to the identity minus R2, what I'm going to find is R1 and R2. Okay, so this is smooth, but of course it has a singularity. G sub s has the singularity along the diagonal. So I always forget to say that, but that's really a pseudo-differential operator. These guys are really C infinity on M cross M blown up along the diagonal. But again, I'm going to put this in quotes, and what this C infinity really means, and remember my third aphorism from yesterday, my third aphorism was smoothness has to be interpreted liberally. Okay? So the right way to think about smoothness is in terms of having these asymptotic expansions with smooth coefficients. Okay? So the right notion is space APHG. This is the space of polyhomogeneous functions. Okay, these have smooth expansions. And I'll give a slightly more formal definition, but these relate very much to the conormal distributions that Alex was talking about, and that Alan was talking about in the last lecture. And so they're the right replacement for smoothness. So on a manifold with boundary or corners, polyhomogeneous functions are the things to look at. Now, I think many people have disclaimed this terminology. It's terrible, polyhomogeneous, but it's stuck with us, so we can blame Hermander. So, okay. Because he wrote it down in his book. Okay, so what I'm claiming here is that if I look at this particular formula and look at these particular things, what I'm going to get is functions which are as nice as possible on this weird space. So remember my dictum from last time, we have analytic complexity. So if I'm looking just at this space, where here's x tilde and y minus y tilde, the diagonal, then all sorts of chaos is happening right here. We can't really see very well. When I blow it up, I can see it, and it's smooth in this extended sense of smoothness. That's the whole point. Okay? Okay, so, what I did here was I didn't have to do much work because I kind of knew the answer in each region, and I glued them together. So this is not the full zero calculus parametric construction. That comes next, almost next. Okay, so any questions about this? So the claim is that, let me just say one more time, this G sub s is smooth. Its expansions on the left and right faces and on the front face are exactly the same as in the whole hyperbolic space setting. So when I wrote down, for example, this regularity theorem, it's still true. Right? Still true. And so, for example, elements of the null space have a specific rate of decay, or if f is in C infinity 0, I get the same type of expansion. But of course, these coefficients now, this one in particular, is going to depend on the perturbation v. Right? So that's, of course, the interesting bit of scattering theory. It's not free space scattering. Okay, now that was my second case. Let's speed up a little bit. So the third case is what I talked about, Hn mod gamma. So this is sort of a further localization. So I'm interested in what I call convex cocompact quotients. Okay, and so what this is going to look like, so I'm not going to give you a full lesson in geometry, but let me just say that the ends of these near infinity look like the large end of hyperbolic space. So I might have something that in the surface case looks like this. There might be some sort of topology, but each end is flaring out exponentially. Now, the two-dimensional picture is a little bit deceiving for the following reason. It turns out that in 2 dimensions, each of these ends I can sort of cut off and I can write as a warp product. So each of these ends is going to look like dr squared plus sinh squared r, or let's say cos squared r, d theta squared. There's going to be some geodesic right here, and it looks like a warp product, which is expanding exponentially off of that end. It looks like a half cylinder. Okay? 2 dimensions is very, very special, of course. In 3 dimensions, it's quasi-isometric to that, but it's far from a warp product, so it's a much more complicated geometric structure. So it's going out exponentially, but in 3 dimensions, the cross-section might be some surface of genus 2, and it's flaring out exponentially. Okay? Now, there's a technical definition of what these convex co-compact quotients are. These are sort of, well, co-compact is a little bit misleading because it makes you think that the quotient is a compact manifold. It's not. It's clearly non-compact. But something inside of here is compact. There's something called the convex core, and there it is. That's the quotient of the convex core. That's a compact set. Okay. Anyway, so I'm not going to describe the geometry of that too carefully now, but just to say this is a very interesting class of hyperbolic N manifolds. And so the question, so this was something I thought about many, many, many years ago, was how do I understand the resolvent on these sorts of things? So this was work I did with Richard Melrose back in the mid-'80s, I hate to say. And so at that point, what had happened was, so people had understood, hyperbolic space, of course, since, Ptolemy or something, Archimedes. These perturbations, certainly various people, so Lax and Phillips had sort of studied this. Ralph Phillips had some students who worked out the scattering theory in this sort of very specifically. And there was something called the Ince method in scattering theory that Peter Perry had been working assiduously to try to solve. But it turns out that these parametrics methods really provided the definitive answer. Now, a lot of people have done work on this. I will describe some of it right now, but I want to mention Joshi Sabaretto, Colin Guillermou, and, well, a lot of other people, but maybe those are sort of key figures who sort of helped develop the scattering theory in this type of setting. And Peter Perry, I should say, did some stuff using this method eventually, and so on. So let me tell you why it's still a slightly easier problem. So now I have this sort of funny manifold. Let me redraw it here. So this is very non-compact. These ends are meant to be going out to infinity, where the ends are flaring out exponentially. Okay? So the first step is I pass from M, which is H n mod gamma, to its compactification, M bar. This is a manifold with boundary. So this is already sort of embedded in the definition of convex co-compact, that there is a compactification of this as a manifold with boundary. Okay? There are other types of hyperbolic quotients where it's much more difficult to compactify, but for these guys, it's actually possible and fairly straightforward. Okay, second step is I look at M bar cross M bar blown up along the boundary of the diagonal. So I can only draw the same picture as I did before. Here's M bar cross M bar, x, x tilde, and now I really have to think of y and y tilde being separately. I can't sort of use translation invariance in the y variable anymore. I still have the same manifold at the corner. So here's the diagonal, and of course, I have a pseudo-differential singularly along the diagonal, but it's going to scrunch down here. Something bad is going to happen, and what I'm going to do is I'm going to blow up that point. Okay, so the picture I get, well, this is the only picture I know how to draw, quite frankly. But I'm pretty good at it, right? So I've been practicing for years. So the point is that I blow up this same description, this boundary of the diagonal. That's exactly x equals x tilde equals 0, y equals y tilde. I get this thing. This is now a manifold with corners. And the theorem is, let me see, I can move up here. Okay, and so so I have this M2, so I'm going to shorten this as M20 is this blow up here. Okay, so this denotes this space. So the theorem is that if I take Laplacian minus s times n minus 1 minus s on Hn mod gamma, I take G sub s, which is its inverse, its resolvent, right? Then the claim is that this is an element of psi minus 2, I'm going to put some funny notion here, 0. Okay, I'll tell you what all these symbols mean. Okay, and this is meromorphic in S. Okay, so to say more clearly, Here's the S-plane. Here's this critical line. I start off with this function, and it's completely well-behaved except for the possibility of a handful of poles down here, which for the function case don't occur, but for forms they might occur. So there's a pole right there, but there's nothing here. But then it meromorphically continues to this side. And I'll tell you a few modifications to say that quite correctly. So this is a theorem I proved with Richard Melrose back in the Pleistocene. And what do all these symbols mean? So first of all, it's a pseudo-differential operator of order -2. That just tells you that on this, oops, there's my space. Okay, so here's the space. So what do all these adornments mean? So psi -2 script e sub 0. This 0 means I've done this blow up. Okay? It refers to the following fact. This is called the zero calculus, which means that I have operators which are based on differentiating with respect to the vector fields x dx and x d by dyi. So I introduced these last time. This is called the space of V0 vector fields. So namely, on a manifolded boundary, like M bar, oops, I erased it, M bar, right? I look at all vector fields which are smooth in the interior and vanish at the boundary. They're spanned over C infinity by that. I take an elliptic combination of these vector fields. This operator is one of them, this Laplacian minus s times n minus 1 minus s. So I have an operator, this Laplacian minus s times n minus 1 minus s is a differential operator in this zero calculus of order 2. And it's elliptic. Okay? So that's what the 0 means. So the parametrics is going to live on this space. And then this E actually has, so I'm going to give you terrible notation and explain what it means. So this E looks like a triple, where the triple is, so this is the face 1, 0, this is the face 0, 1, and this is the face 1, 1. So the front face, the left face, and the right face. We just have to keep track of the various boundary hypersurfaces. All this is going to tell you is this pseudo-differential operator, its Schwartz kernel has a standard singularity here. It's polyhomogeneous. It has smooth expansions as I go to each of these 3 boundary faces. Right? And this E10 tells you which exponents occur in the boundary face to the left. This E01 says which things occur to the right. And the E11 corresponds to what exponents occur. So if I were to write those out in terms of what we discerned before, right? So E10 is going to be, S, S plus 1, S plus 2, et cetera, and then n minus 1 minus S, n minus S, n plus 1 minus S, et cetera. So these are all the exponents that occur at the left face. This actually is self-adjoint. So this is E01 is going to be the same thing, and E11 in this case is just, it's smooth up to that face. So that's a very particular case. I've listed the exponents that can occur in the expansions here and here, and the expansions here. And remember, these things are just smooth. They just have funny exponents, but you should think of them as smooth. Okay? And I think I've explained all the bits of notation here. Okay? So living in this funny space of pseudo-differential operators, the resolvent of the Laplacian is meromorphic. Okay? Its poles are, of course, interesting bits that, Matrix can tell you all about, and has or will. And of course, there may be other things. Coulomb-Guillemot's contribution was, in fact, really understanding the nature of some of these poles where it looks like they should be much more complicated than they are, and he found the right geometric conditions for understanding that they're just, isolated poles. Jocelyn Sabredo had understood other aspects of some inverse problems and understanding the Poisson operator in this setup and so on. Now, let me describe how you prove this in this simple case, because it's not still the full zero calculus yet. So this G sub S, how do I find it? Well, so I have this manifold, and the point is that this manifold is sort of localized. So there are these various ends, and what I want to do is I want to cover the manifold by neighborhoods. So I'm going to choose an open cover, Uj, of M bar, so that, when I'm at infinity, so here's a neighborhood of infinity, I want it to look just like, there's one of the UJs. This looks like a little block, and that makes sense because this thing looks locally exactly like hyperbolic space near every point at infinity. So that's what's simpler about Hn mod gamma itself. So if I localize near a point at infinity, it looks exactly like hyperbolic space, no higher order perturbations. The perturbations are all kind of global topological perturbations. Okay, so I'm going to do the same following thing. For each uj, I'm going to choose an inverse gj. This is an inverse for Laplacian minus s times n minus 1 minus s. Okay, now the point is when I actually say an inverse, remember every one of these neighborhoods, uj, can be thought of as a neighborhood inside hyperbolic space or its closure. So either uj is an interior neighborhood, it just looks like a ball inside of hyperbolic space, or it looks like a ball around some point at the boundary. So every point locally looks just like a neighborhood of hyperbolic space. I have my favorite formula for what the inverse in hyperbolic space looks like, and I just localize it to this. Okay, and so what I'm going to do is I'm going to set g tilde sub s is equal to the sum, just like I did before. I'm going to choose partitions of unity chi j and then extend them a little bit to call those chi j tilde. I write down this formula, and I do the same computation I did before. So I'm going to write this as Laplacian minus s times n minus 1 minus s applied to gs tilde, and I'm going to get a bunch of different terms. It's going to look like identity plus some smoothing operator. And you can check that where does the bad stuff of the smoothing operator come about? Well, for example, I might have the commutator of Laplacian with chi j tilde, gj chi j. Let's examine that term. Okay, this is one of the error terms. Let's examine that term. Well, the point is that it's that I have this chi j tilde of x and y. Z is equal to x and y. I'm looking near a boundary, of course, where that's sort of more interesting. And then I have this Laplacian in x and y acting on it, times gj of x, y, x tilde, y tilde, times chi j of x tilde, y tilde. That's this error term. Okay? What does this thing look like? Well, remember the Laplacian is built out of x dx's and x dy's. Remember, it just looks like a polynomial in those guys. Every time I apply one of these things to chi j tilde, it stays smooth and bounded. Nothing exciting is happening. It's not getting worse. Okay? So I'm taking something smooth and bounded, and I'm applying it to something which decays very nicely. So in fact, what this thing is, of course, this is going to be a, well, so I'm looking at actually the commutator. Let me sort of be clear. So I'm going to get a first order operator. Its coefficients look like these vector fields applied to chi j tilde. It's compactly supported, but going down to x equals 0. But the point is that all of those things are smooth down to x equals 0. I'm applying this on the left to this guy. gj already had this behavior that it was sort of decaying at some definite rate here. It looked like, x to the s. S is big, right? It's decaying. What that means is that the error term here, these things have a definite rate of decay. Right? And furthermore, and it's precisely because the support of this is disjoint from the support of this, the error term is supported a long ways away from the diagonal and away from this front face. Okay? So what's really happening, and this is what you analyze in this particular case, is that this error term is really compact because it's smoothing, it localizes you well away from the diagonal, so it gives you lots of decay. Yeah?
So therefore the E is, you just want the G, that one that has the S's, right? Not the N minus 1 minus S's.
Yeah, forgive me, yeah, that's exactly right. Okay, so anyway, the point now finally is that, what I've done is I've now found a very good parametric. So I found this Laplacian minus s times n minus 1 minus s applied to this g s tilde is equal to identity plus this compact smoothing operator. Now, this observation that you could actually use these exactly isometric copies of HN was initially exploited by Maciek to understand some scattering a long time ago. So what Melrose and I had originally done was sort of the full parametrics construction. Maciek observed in this constant curvature case, it really simplifies. Okay? Now, I didn't get an exact inverse, right? I got something identity plus this compact smoothing operator. So there's an analytic step. So essentially what's involved, and I want to say a few words about that before the end of today. What's involved is I've found this operator that looks like I have Laplacian minus s times n minus 1 minus s times gs tilde is equal to the identity minus r sub s. This is somehow this very good remainder term. Right? What I'd really like to do is take g sub s to be g sub s tilde times identity minus r sub s inverse. Right? Now, you can do two things. One is you can show that at least when s is really big, what you'd expect is that this error term is really small. Right? So what you'd expect is that this thing has norm less than 1, and so that this inverse really makes sense just by a Neumann series. But more generally, what you can do is you can approximate this identity minus r sub s inverse by identity plus r sub s squared plus dot, dot, dot. So you take the formal Neumann series. So, and if I can make sense of this right-hand side, and I can take the composition, then I get something that's an even better approximation to this. Okay? So at the end of the day, the parametric construction says, first find this sort of parametrics with a good error term, and then I correct it by doing some sort of Neumann series argument. That'll get you even much closer, and then you have some sort of abstract argument which is going to tell you that you really are Fredholm, and that actually what you'd like to say is that the g sub s actually lives in this space of pseudo-differential operators. Right now, all I've done is shown that g sub s tilde does, but I want to say that the g sub s itself does. Okay, so let me now finally tell you the last step in this whole nightmare, which is I have a genuinely variable coefficient operator. So, and instead of sort of talking about the conformally compact case in general, you can talk about these general sort of asymptotically hyperbolic manifolds with metrics that look like rho to the minus 2 g bar. And local coordinates, I can think of this as dx squared plus some metric tensor h of xy divided by x squared, where this h of xy looks like, you know, hj, let me call it h l sub ij of y times dyi dyj times x to the l. So there's the x to the l coefficient as some metric on the boundary. So there's some sort of smooth expansion in terms of tensors, right? And it turns out this is a very interesting class of asymptotically hyperbolic manifolds. The Laplacian for this G looks like the Laplacian in hyperbolic space plus higher order terms. What that means is that this is true in the space diff2, 0. Namely, if I write out the Laplacian, it's going to look like aj of x, y, x d by dx to the j, x d by dy to the alpha. So it's going to look like some combination of these vector fields, these special vector fields, x dx and x dy. The alphas are multi-indices. These aj alphas are, you know, smooth coefficients. They're smooth down to x equals 0. They're determined by the Taylor series expansion here and so on. And if I take the leading term of the Taylor series here, it's the Laplacian in hyperbolic space. Okay. Okay, so finally, in the last several minutes, let me tell you how the full parametrics construction goes. So unlike the previous cases where I kind of can know or guess the answer, I say, well, this is living on some manifold M. This manifold now can be much more general. Take an arbitrary compact manifold with boundary. I can put a metric like this on it. Now, this is not a geometrically uninteresting thing to do. As I said, there's a really interesting active area of studying Einstein metrics of this form. These play a really interesting role in mathematical physics and conformal geometry. So let's suppose I have this arbitrary compact manifold with boundary. I have this metric G on its interior. Okay? And I want to invert this operator or its spectral version, Laplacian minus lambda. So step one is I form this space, M2, 0. This is a canonical description. I didn't need anything special about hyperbolic space to do it. I just take M cross M and I blow up the boundary of the diagonal. Okay? Yeah, yeah. Goes without saying, right? So you compactify M as a compact manifold with boundary. The operator extends smoothly to the boundary and vanishes there. The metric is singular at the boundary. So thank you. Good clarification. Okay, so that's first step. So here's this picture. And now I'm going to sort of draw geometrically what the parametrics should do. So I'm going to write the parametrics G as a sum, so this is G tilde, as G0 plus G1 plus G2. It's going to look like 3 terms. And the whole point is the geometric oomph here, the geometric extra complexity, allows me to localize in interesting neighborhoods. So step 0, this guy, is I do, with all due deference to the weight of history, the trivial thing, which is I take the elliptic parametrics construction along the diagonal. So symbol calculus, just what you learned yesterday morning. Okay? So this is the very classical description, nothing more. The point is it's happening along the diagonal, and here's the interesting thing. Even though the operator is degenerating in ordinary coordinates, once I've done this blow-up, it's not degenerating anymore. So my claim is, if you like, I take these vector fields, xdx and xdyi, and I lift to m20. And I get non-degenerate, non-vanishing vector fields. So this process of resolution actually has this huge gain that this operator, which looked like it was vanishing at the boundary, once I've sort of blown up in polar coordinates, it no longer vanishes. Okay? So G0 is I just, take a parametrics which is localized there, and I have an error term, R0, which is localized in the same neighborhood. What is R0? Well, it's a smoothing operator. It vanishes outside of that neighborhood of the diagonal. So I have this Laplacian of G0 is equal to the identity minus R0. R0 now lives in this space, but it's completely smooth. It's localized here. And what does it do in terms of its mapping properties? So if I take R0 and I take any, let's say, weighted L2 space, okay? So I take any weighted space. So delta could be minus a million. This is going to map it into the space with exactly the same weight, but I gain a lot of regularity. I'll call h infinity sub 0. This is with respect to the vector fields xdx and xdy. So the right way to measure regularity in this geometry is with respect to these vector fields. So it's infinitely differentiable with respect to these vector fields, stays in L2 no matter how many times I apply these vector fields, and it decays or blows up at exactly that rate. Okay? Okay, now, again, if you've been reading your Gilbart and Trüdinger diligently, this is just Schauder estimates. These are just scale invariant Schauder estimates. Right? So I've not done anything beyond what was known in the 1950s. Okay? So second step is I now want to solve away this error term. So here's this space, and if I got some extra decay here, so here's this error term, if I could somehow make the error term vanish at this space, then I'd change this x to the delta to an x to the delta plus 1. And morally, I have 1. I've gotten regularity plus extra decay. And that's enough to apply the L2-Arzela-Escole theorem. That gives me a compact operator. Okay? So if I can get some extra decay, which means can I find an error term which vanishes to first order at this phase, then, well, the rest is really just neatening up, but that's the main moral victory. Okay, and here's sort of the final step, how you do it. I just restrict this operator to this front face. So I take Laplacian, restricted to the front face, acting on some mystery operator. I don't know what this G1 is, but I restrict it to the front face. And this is supposed to equal R0 restricted to the front face. Okay, so I have this smooth kernel. I restrict it to the front face. It's just a smooth, compactly supported function. So here's the front face. It just looks like a quarter sphere. And I have a smooth, compactly supported function there. Okay? And there it is. G1 is something I'm trying to solve for. This Laplacian restricted to the front face. Okay, well, if you'll allow me one more minute, here's the Laplacian. When I restricted this front face, I could write this out in polar coordinates, but we'd be here all day, and I'd make mistakes, right? That's a horrible coordinate system to use. Let me use projective coordinates instead. So I'm going to set, I'm using S in a different context. S is equal to x over x tilde. U is equal to y minus y tilde over x tilde. These are coordinates on the front face. If I lift this operator with respect to this thing, so what I'm going to get is aj alpha, x is equal to x tilde times s, y is equal to y tilde plus x tilde times s. X dx becomes s ds to the j. X dy becomes s du to the alpha, s du to the alpha. So what I've done is lift things. It looks like I've made no gain at all, right? Because started degenerate looks degenerate. But then you think s is not equal to 0. S is equal to 1 around here. Remember, s vanishes when x is 0. So this is a projective coordinate system where the S is sort of a coordinate from that front face. So S is non-vanishing in the interior of this face. Yes, thank you. Thank you very much. Okay. When I restrict to the front face, what do I get? So I restrict to x tilde equals 0. That's the front face. I'm going to get aj alpha of 0 comma y tilde, s ds to the j, s du to the alpha. Anybody recognize that? I told you sort of implicitly what that was. It's the leading order Taylor coefficient at a given boundary point. It is the Laplacian in hyperbolic space. This is equal to the Laplacian in hyperbolic space. Okay, so at the end of the day, I have to solve a model problem, and it's the problem I've been solving all along. So the model here is the Laplacian in hyperbolic space applied to some mystery function is equal to a smooth, compactly supported function. So the point is here, this quarter sphere is really just a projective version. It's a stereographic projection of hyperbolic space. It just looks like a half space projected down to a quarter sphere. This operator, once I lift to this double space and restrict to that front face, it's exactly this model operator. Okay? And we know how to solve that problem. Okay? So the point is, this step 2, this finding this G1, we've solved already. Okay? Okay, so let me just sort of summarize where we're at. This G2 is sort of solving things at the left face over here. That makes things a little bit better, but that's kind of unnecessary. We've already got something, even with these 2 steps, that gives you a compact remainder term. We're done, and we can actually prove that general theorem of meromorphy, the resolvent at this stage, if you work hard enough. But the key is we have 2 models. Along the diagonal, we have the diagonal symbol. We have sort of the classical pseudo-differential calculus. We have another model which is interlaced with that. It's subsidiary. It's a secondary model at this front face, and it is exactly the model problem for this thing. It's the hyperbolic Laplacian. So to say that an operator is elliptic in this calculus, you need both things to be invertible. You need the diagonal symbol to be invertible, and you need this normal operator in the front face to be invertible. If those both are, then you can find a parametrics with a compact remainder. Okay, so I've beat this problem to death, more or less. Tomorrow what I'm going to do is tell you, this is one part of a big universe of different types of degenerate operators and applications. I want to mention more names of people who have contributed to this, but I want to talk about sort of a much broader set of types of operators. But the scheme is always the following. I take M, I take M cross M, that's where the parametrics is supposed to live. I blow it up according to some dark art, and I find a good thing that may have multiple boundary faces. So for example, suppose I'm trying to look at the Laplacian on a polyhedron in Rn. That's a problem that we're all deeply interested in, right? It's harder than, it's more complicated than you think. You have this polyhedron cross itself. It has corners of very high codimension. You have to blow up a lot of stuff. And then you have a whole sequence of model problems that you have to solve. This systematizes that, so it just reduces to a bunch of model problems that you know and love. Okay, sorry for going over time. Yeah. Yeah, so part of this, which I haven't sort of said, so when I say that something is polyhomogeneous on a manifold with corners, it has a precise definition. So A, it's conormal. So it's a stable regularity with respect to the vector fields which are tangent to the boundaries and corners. Secondly, it has an expansion, which is product type near the corners. So let me just sort of say very briefly, suppose I have something which is smooth in polar coordinates, and I was misfortunate enough to look at it in ordinary rectangular coordinates, but it's really smooth as a function of r and theta. Well, so somehow its behavior is going to be really kind of messed up. There's not a Taylor series approximation at the corner. But if I blow up, so here's r, here's theta, then it's smooth in r and theta. And it's smooth up to the corners in the ordinary Taylor series sense. So we just mean a generalization of that where you have product type expansions of the corners. And that's what's really important. So, again, sort of one of the basic principles of microlocal analysis is you restrict things to, you work in a category of things where you can sort of solve iteratively. You can get rid of all the error terms by some sort of iterative construction. And this is what allows you to do that. Yeah.
So if you were to sort of go into some other setting of
Yep.
a different symmetric space, it seems somewhat clear how you try to look for your new models.
Right.
But you had mentioned that for the resolvent, there's this sort of funny structure of the poles. Is there some way to see that just like geometric microlocal?
Well, so the structure of the poles, I was wanting to say, so it turns out that hyperbolic space itself in even dimensions, when you continue the resolvent, it has poles of infinite rank, okay? And something that Richard and I missed umpteen years ago, and Coulomb sort of cleared up for us, was that if you don't make special assumptions on the metric, which tells you something about the coefficients of this thing, then what you're doing is you're applying the analytic Fredholm theorem on a domain like this. So you have something which is, you know, you have a sequence of poles here. You're analytic on a punctured complex plane, right, basically. And the point is when you apply the analytic Fredholm theorem, you have a sequence of poles which may arise, but then you might have a whole sequence of poles which cluster at these things. So, you know, it's like an infinite order pole splitting apart into a cluster of, you know, a whole bunch of finite rank things which converge to it. So how do you make sure that doesn't happen? So Coulomb found the right conditions.
But this is something you can see sort of at the level of hyperbolic space.
No, it's actually something about the higher, so it's not a hyperbolic phenomenon. These poles really exist in hyperbolic space, and that's the problem, right? But if you look at the higher order Taylor series expansion, then it turns out that you can find exactly the conditions for which they don't think. And I should advertise, so Andras has an alternate approach which doesn't involve any of this nonsense, which sort of sidesteps, I mean, you know, it produces the same issue, but he has a much nicer kind of purely microlocal description of this, so.